In this media, you will learn about the load characteristics of synchronous motors. Behavior of synchronous motor on loading. Due to increase in the load torque demand, the speed of DC motor or induction motor falls as soon as it is loaded. Hence, more current is drawn by the motor in order to create more torque. This torque satisfies the load, but the speed of the motor decreases. In the synchronous motors, the speed remains constant at all times, and this speed does not depend on the load condition. In a DC motor, the armature starts to produce an EMF once the motoring action begins, and this EMF opposes supply voltage, and hence it is called as back EMF, denoted as E sub B. The value of E sub B for a DC motor is given as E sub B equals phi times PNZ over 60A. P, the number of field poles. Phi, the flux produced per pole in Weber. Z, the total number of armature conductors. A, the number of parallel paths in armature. N, the rotational speed of armature in revolutions per minute, RPM. For a DC motor, armature current I sub A is given as I sub A equals V minus E sub B divided by R sub A. Here, R sub A denotes the armature resistance, and V denotes the supply voltage. Even in synchronous motor, when the rotor starts to rotate at synchronous speed, the fixed stator conductors cut the flux developed by the rotor, and thus EMF is induced in the stator. The only difference in synchronous motor is that the conductors are fixed and flux is rotating in nature. According to Lenz's law, this induced EMF opposes the supply voltage. We call this induced EMF as back EMF while dealing with synchronous motor, and this EMF is denoted as E sub BPH, in other words, back EMF per phase. The equation of the back EMF per phase is given as E sub BPH equals 4.44 K sub C times K sub D phi F times T sub PH. Here, K sub C denotes the coil span factor or pitch factor. K sub D denotes the distribution factor. F denotes the frequency of the supply voltage. T sub PH denotes the number of turns per phase, and phi denotes the flux produced per pole. Since the motor always rotates at synchronous speed, it has a constant frequency, and hence magnitude of such back EMF can be easily controlled by altering the flux phi generated by the rotor of the motor. The construction of the stator of synchronous motor is similar to the construction of armature of a three-phase alternator. Hence, the impedance of the stator, Z sub S, is also known as synchronous impedance of synchronous motor. Ideal condition on no load. The ideal condition on no load can be assumed by ignoring several losses in the motor. In this case, V sub PH and E sub BPH are always equal. In other words, V sub PH equals E sub BPH. Under this circumstance, the magnetic locking present between stator and rotor is in such a way that the magnetic axis of the stator coincides with the magnetic axis of the rotor. This magnetic locking occurs during the lossless condition, and thus the synchronous motor is said to be an ideal condition. Synchronous motor on no load with losses. We have already learned that the magnitude of E sub BPH and V sub PH are equal, and this can be done by controlling the flux. In this circumstance, the magnetic locking present between stator and rotor is in such a way that the axes of two magnetic fields have a small angle difference. Here, the rotor magnetic axis lags the stator magnetic axis by a small angle called load angle, power angle, or angle of retardation, and noted as delta. This angle difference, delta, decides the amount of current needed to produce the torque in order to supply various losses. The magnetic locking between the stator and rotor is still present, and the rotor rotates at synchronous speed along with the rotating magnetic field in order to preserve the angle difference between both the field axes. The flux lines between the stator and rotor extend because of such retardation of rotor axis with respect to the stator. Although the magnitudes of E sub BPH and V sub PH are the same, E sub BPH will not be positioned in exact opposition with V sub PH. It will get displaced from its original position by an angle delta. Therefore, the vector difference between E sub BPH and V sub PH gives rise to a phasor, OB, called as resultant phasor and represented by E sub RPH. This resultant phasor decides the quantity of total current, I sub APH, drawn in order to create the torque that meets several losses existing in the synchronous motor. Under no load condition, the angle difference delta is very small, and hence the value of E sub RPH is also small. Synchronous motor on load. Whenever the load on the motor is increased, the load angle delta is also increased, but the motor remains at synchronous speed. Even though the magnitudes of E sub BPH and V sub PH are equal, displacement of E sub BPH from its ideal position increases as the load angle delta rises. The synchronous impedance is always constant, and hence the magnitude of current I sub APH drawn by the motor rises as the load increases. This current creates the required torque that can satisfy the increased load demand and maintain the magnetic locking. In no load condition, the current drawn by the motor is very small, as the load angle delta between the magnetic axes is small. When the load is increased, the load angle delta is also increased in order to keep up the magnetic locking condition. When delta is increased, the flux lines between the stator and rotor extend. This deteriorates the force that keeps up the magnetic locking, though the torque generated by the motor rises. When the load angle delta goes beyond 90 degrees electrical, in other words, half a pole pitch, the extended flux lines break. Thus, the magnetic locking between the stator and rotor vanishes when the load angle is above 90 degrees electrical, and the motor also gets out of synchronism. So, the maximum torque is produced by the motor at delta equals 90 degrees electrical, and this torque is called as the pull-out torque. Thus, you have learned about the load characteristics of synchronous motors.